שלום רבותיי, ברוכים הבאים. נא לכבות את הטלפונים הסלולריים. אני מבין שהאנגלית הפחידה חלק גדול מהקהל הקבוע שלנו, אבל לפחות הנבחרים הגיעו וייהנו מההרצאה, מהאירוע. אני מניח שגם העומס של החודש האחרון, עם כל שבוע הרצאת מדוע, נותן אותותיו בקרב הקהל המתעניין. אבל יש פה, אני חושב, קהל מתאים לאירוע. אנחנו נפתח כרגיל בפתיחה מוזיקלית, ויש לנו היום אוסף שירי ג'לאל א-דין רומי, הפייטן בנימין יעקוביאן, נגן אתר מנוצ'ר בלזאדה. בבקשה.
هر جا که قدم نهی میبینیم تو را، در مذهب عشق روا کی باشد، عالم تو نبینیم و نه ببینیم تو را. אהובי, זאת הקרבה שלנו, שלי, שלך, כל מקום בו תדרוך, שם אהיה למדרך רגלך. מה מוזרים החוקים בדת האהבה? הייתכן? את עולמך אני רואה, אך לא אותך. אני יכול להיפרד מכל אחד, חוץ מהאחד שבתוכי נלכד. לי כל אחד להעניק שמח, הביאו לי אחד שגם לוקח. על הלילות לא נדבר, כי בימים שלנו אין לילות. בדעת יש אהבה, אבל לאהבה אין קשר לדתות. האהבה היא ים, ללא חופים, ללא גבולות. ובו רבים טובעים בזעקה. בכל העולמות ראיתי עיניים, ובכל עין לפחות עולם אחד. מי שפוזל רואה הכל כפליים, אבל אני רואה בכל ריבוי אחד. הוא בליבי תמון, ובו תמון ליבי, רק הוא בדם עורקיי, בתוך גופי. ואין יותר לא אמונה ולא כפירה, כי הוא כל היקום, ומלבדו אין לדבר קיום. در قلب منم در قلب اونم. فقط او در شعرگم هست، در داخل بدنم. نه بیشتر ایمان است و نه کفر، که او عالم هستی است، بدون اون بقا نیست.
תודה רבה. הרצאת המדוע הבאה תהיה בשבוע הבא, 4 ליוני. פרופסור אילן סלומון מהמחלקה לגיאוגרפיה יבוא לספר לנו על אחת הבעיות המעניינות ביותר בתחום התחבורה בארץ וגם בעולם, על הוויכוח בין רכבות, פתרון של רכבות לפתרון של כבישים, ואיך זה מתקשר לפוליטיקה. הרצאה שמבטיחה להיות מרתקת. והשבוע יש לנו הרצאה שונה מהפורמט הרגיל, לא רק בשפה האנגלית, אלא בכך שהיא הרצאה שאנחנו קוראים לה הרצאת מרכז איינשטיין. ואני אזמין אל הבמה את פרופסור חנוך גוטפרוינד, נשיא האוניברסיטה העברית לשעבר, שהיום הוא מנהל מרכז איינשטיין, והוא יספר לנו קצת מה זה מרכז איינשטיין, ואחר כך יציג את המרצה של היום. בבקשה.
היות וההרצאה היא באנגלית כולה, אני ישר אתחיל באנגלית. And it's my pleasure to introduce Professor Sandra Faber as the first visitor of the Einstein Center. But before my words of introduction for the speaker, let me tell you a little bit what the recently established Einstein Center at the Hebrew University is. As you all know, last year the whole world, the Hebrew University included, marked and celebrated the 100th anniversary of Einstein's miraculous year. And in this context, the Hebrew University worldwide was involved, in fact was a key player in producing a large number of exhibitions, workshops, and a variety of events bringing again to the public and academic light Einstein's legacy. In this context, the Hebrew University had a specific collaboration with the Ministry of Science of the Federal Republic of Germany, and as a gesture of appreciation, gratitude, the Ministry of Science of Germany decided to establish and to generously support at the Hebrew University this Einstein Center that in the years to come will bring together scholars, groups, visitors, do workshops on a variety of topics that somehow are connected with Einstein's life, work, and achievements. You will not be surprised that the major part of that is physics, and we'll have two groups participating in that. One is the cosmology group, headed by Professor Deckel, and the particles group, the elementary particles group, field theory group, Professor Eliezer Rabinovitz. Of course, Einstein's fame stems from his work in physics, but having said that, one should also mention that he was a prolific writer, a person who was involved, participated, wrote, and was active on every issue that was on the agenda of mankind. And to mark that aspect of Einstein's legacy, the Einstein Center will also include a humanities section that will study, explore the subjects of interplay between science and culture. Will also include a social science section to be headed by Professor Raymond Cohen, who is here, that will explore such topics as ethics in international order. And each case will have, as I said, workshops, will bring prominent visitors like today, and the idea is that in addition to these visitors talking to the scholars, to their academic counterparts, we shall have in each such case a public lecture also to share this legacy with the general public. I'm very pleased that we have this occasion to host Sandra Faber here. Now, as you know, Professor Faber is a professor at the University of California. She is a cosmologist, and that means that she is interested in the development, the large-scale structure of the universe, specifically in the formation of galaxies. And I understand that at the entrance you receive this sheet, which gives you a very impressive list of achievements, prizes, affiliations to very prestigious societies. So let me tell you something, a few things that are not on this list. Now, as you know, in order to have some information about the universe, one has to observe first. So we need astronomers who observe, to collect data, and here a lot of experimental sophistication is needed in order to to struggle with all the problems of resolution and interpretation of data. So we need observers. In order to observe, we need very powerful instruments. And in order to build these instruments, you need resourceful engineering skills. But whatever you observe, and as many data as you collect, they are meaningless if you do not have a conceptual framework. So you need observations, engineering, and theory. Now, what is remarkable, that today we have all these in one person, and that is unique, and that is Sandra Faber. But there is one thing which I would like to add, which for us is even more relevant than all that. Professor Faber has a long-standing relationship, cooperation with Israel science, with Israel astronomy, specifically with the Hebrew University. We had the pleasure of hosting her at least twice that I know about in the last few years, and she specifically cooperates with the cosmology group headed by Avishai Deckel, and it is a real pleasure to welcome you here today, please.
Thank you so much. Believe me, the pleasure is all mine being here today, and the thought of being the very first Einstein lecturer is somewhat overwhelming. The only comfort I have is that if Einstein were here today to listen to this talk, and of course my talk is really a review of what hundreds, if not thousands, of astronomers and cosmologists have been doing for the last 50 years, but if he were here to listen to this talk, I think he would say, you guys have done a pretty good job of putting together basic physics and coming up with a story of how the universe evolves. And of course, he was very interested in that subject, so I think he'd be delighted to come back today and see how it all fell out. So I'm going to tell you that story in a fairly factual way at the beginning of my talk, but then we know that Einstein was a very philosophical scientist as well. Professor Gutfreund has been reminding us of that. And therefore, at the end of my talk, I'm going to broaden out the subject a little bit because I'm going to start talking about things that I know no more of than you do. In other words, having set out the cosmic story, let's all talk together about what that means for how humanity should behave, if it means anything. So at the end, we'll mix together some science and some morality and some perhaps even theology to see where this story should be pointing us for the future. So, this is my topic, Cosmic Steps on the Road to Intelligent Life. The universe is 13.5 billion years old, and the story I'm going to tell you today takes up about 9 billion years, the first 9 billion. I hope you'll pardon me for not going all the way and telling you about the whole 13.5 billion years, but I'm going to stop with the formation of the sun and our solar system. And I hope that you'll have another lecture in the future that will involve a geologist and a biologist to come and talk to you about what happened in our solar system over the last 4.5 billion years that led to us. It's a very, very interesting story, and if you want to ask me a couple questions about it, I know just a little bit, enough to say a couple of interesting words. But I'm a cosmologist, and I'm going to tell you about the space of time from the Big Bang to the formation of our solar system. And that's what I call the cosmic steps on the road to intelligent life. So before plunging in here, let me just pose a question. I don't know if you've ever thought about this. The question is, why is there structure in the universe? I'm not really asking why is there anything in the universe at all? Why does the universe have matter, light, and so on? That's an even deeper question. I'm posing the question for you, why do we have lumps in the universe? A lump is like the Earth, a planet, a star, a galaxy. And between these lumps, space is rather empty. So why does the matter in today's universe organize itself into lumps? Why isn't it absolutely perfectly smooth? Well, that's one of the most interesting stories of cosmology, and that's how I'm going to start my talk, because understanding the formation of those lumps lays the foundation for everything else that happened later. As you will see, the key force in forming those lumps was the force of gravity. The universe began expanding just after the Big Bang, and at that time we believe it really was very smooth. But there was a process just after the Big Bang at something like 10 to the minus 35 seconds. What is that number? That's 1 over, in the denominator, 1 with 35 zeros. So that's an incredibly small number, 1 over a huge number. This fraction is tiny, tiny, a tiny fraction of a second. Something very, very interesting happened. And the thing that happened then was a process that took a universe that was smooth and made it ever so slightly lumpy. Not very lumpy, only 1 part in 100,000. But there were peaks and valleys in the mass distribution at that point, after this process. So take that kind of universe and let it expand, and what happens? Around a peak, there's a little bit of extra gravity, and that part of the universe draws more matter in. In a valley, there's less gravity, and that matter can flow out. So there's extra expansion in the valleys and less expansion around the peaks, and that means that the peaks are getting stronger relative to the valleys. We call this a gravitational instability. It's the gravity of the matter in the peaks that's driving this process. And this is the basic process that made lumps. So let's look at the first slide to watch a movie. Cosmologists now are making models of this process in the computer. Okay, so I'm going to start my movie and stop it so that we can look and see what we see here. This is a cube, which is supposed to be a completely typical random cube in the universe. And we're looking at it at some early time. In fact, I told you a little while ago that the universe was 13.5 billion years old. We're looking at it now when it's only 100 million years old. It was much smaller than it is now. And in fact, this number here in the corner, don't get too caught up in it, but that number is telling us how much smaller the universe was at this time. And this number is going to become smaller as we go forward in time. And when this number equals 1, that's today. So you can watch that number and get some feeling for how big the universe is as the movie evolves. So, as I say, this is a typical cube carved out of the universe at this very early time. And the matter points have been arranged in it so that they aren't completely smooth and uniform. They're ever so slightly clumpy to mimic this process that I was telling you about. So there are little density waves and ripples in this cube at a level of about a part in 100,000. And what the movie is going to show us is how gravity operates around the peaks to create peaks which then merge with other peaks. And that's the structure, that's the root of galaxies as we see them in the universe today. Now, there's only one crazy thing about this movie. The universe is expanding, but this cube doesn't get any bigger. That's because the people who made this picture, as the cube got bigger, they stepped back their point of view so that the cube always just fills the screen. But actually, during the movie, the cube is getting 30 times larger in terms of real size. And so at the end of the movie, this cube is much bigger than this building. Okay, so now let's take a look at this. Here's our simulation taking off. First of all, we get an idea of how the matter is distributed. And now we can see those peaks taking shape. And you see as the cube rotates, it's rotating to give you some idea of the three-dimensional structure of these peaks as they are forming. And if you kept your eye on a pair of peaks close together, you would see them later in the movie fall together to form a bigger peak. This we call hierarchical clustering. We're making small peaks in chains which then fall together to make bigger peaks. And the largest globes that you see in this movie, structures about that size there, are superclusters of galaxies. And the smallest globes that you see were about the size of a single galaxy. So here's another movie which shows the structure, I think, even better. This is a slice through one of these cubes. And the rendering is particularly nice to watch the structure taking place. So this movie starts when the universe was about 10 times smaller than it is today. And as we saw before, little lumps like this form, and then they fall into bigger lumps. This movie is on a loop, so it's just going to repeat. It takes about 10 seconds to repeat. And you can see little pairs of lumps falling together to make bigger lumps. So the smallest thing you see in this movie is a galaxy like our own Milky Way, and the galaxies are clustering together to make bigger clusters of galaxies. So if you're very ambitious with a big computer, you can make a model of the entire visible universe. And that's what this is a model of. This one is not evolving. This is a fly-through today's universe, and it gives you some feeling for the vastness of the structure that we are currently embedded in. We're going down and down and down, and as we go to smaller and smaller scales, clusters of galaxies appear, and then they break up into smaller lumps, which are smaller galaxies, and so on. This movie is centered on a very big cluster of galaxies right here. And we're going to fly into it, and we'll see that embedded within it are individual galaxies. So as we're flying along here, if you see a lump that's about that size, that's about the size of our own galaxy, the Milky Way. The Milky Way, our Milky Way, is not in a cluster like this, but we see around us many galaxies that are in clusters. So you can see, as we watch this movie, how hard it would be to do this calculation in order to model simultaneously the universe on very big scales and yet have enough resolution in the computer to show this very fine scale structure. Okay, so we now actually have before us about 80% of the story of the formation of large-scale structure. It was a feature of this process right after the Big Bang that made density ripples that were very big on large scales and ripples that were on small scales and all scales in between. We can see evidence of these multiple scales when we actually make observations in today's universe. Here we are at the center of this diagram, and we are looking out and observing other parts of the universe far from us. This is something called a redshift survey, and there are 220,000 galaxies that have been mapped here. So the way you do this is you look in a direction, you see a galaxy, and you measure its distance. So here's the direction, and you plot the dot at its estimated distance from you. And you do that 220,000 times, and you can make a map like this. Each small dot is a galaxy, and we are here. And to give it some scale, about 1/4 to the edge of the visible universe is as I've shown it. So the point of this is to see that there are very large waves that make large clusters, like this, and they are separated by voids, empty places like this, and then embedded within this are much tinier things called galaxies. But all of this structure, the large and the small, all came from these original density ripples that were imprinted on the universe at 10 to the minus 35 seconds. And I'm going to come back at the end of my talk and talk about where they came from. Einstein would really like that part. So the large waves make the large-scale structure, and the small wavelets make individual galaxies. Okay, so now let's say some more about galaxies. Up to this point, I've been cheating you a little bit. I've been speaking as though the movies that we're watching are actually visible galaxies, but that's not quite true. Here is a visible galaxy. It happens to be an edge-on rotating disk, and we now know that such disks are surrounded by halos of invisible matter that are 10 times larger and 10 times more massive than what we can actually see here in the form of stars. So we have a name for this invisible larger matter, and we call it dark matter. And the movies that I've been showing you are actually movies of the dark matter. We don't fully understand why this matter, which makes stars, what is that matter? Well, I call it ordinary matter. It's the matter that the Earth is made of. It's the matter that this room is made of. The matter from the periodic table, oxygen, hydrogen, carbon, and so on. That's the stuff that somehow magically has sunk to the center of this dark halo to make this galaxy. There's been a separation of the two different kinds of matter, and this is something that Avishai and I and collaborators are studying in detail to know why this happens and why we get the galaxies that we do. But that we don't really need to be concerned with those details for the broader story that we're dwelling on today. But I do want to say a lot more about galaxies, because galaxies are a very important way station on the road to intelligent life. No two galaxies are exactly alike. Here's a gallery of pictures of galaxies, lots of them taken with the Hubble Space Telescope. This one's interesting. This is actually two galaxies. They're transparent. You can see through them. And so there's one spiral galaxy in the foreground projected on top of another galaxy in the background. Here's an absolutely normal-looking regular galaxy. Here's a highly irregular galaxy that is a train wreck. It's running into another galaxy and being pulled apart. And here's a relatively normal galaxy that is full of dark particles, which we call interstellar dust grains. Those dust grains are opaque to light, and they are generated in the atmospheres of a certain kind of star and blown out into the interstellar medium, and we see them in silhouette against the starlight. Now, even though there's a bewildering array of different kinds of galaxies, they do divide themselves up into two basic families. and one family is roundish, featureless, smooth, and spheroidal shaped. And here are some pictures of those. Here's a cluster of galaxies. I told you that there were clusters, and here's an example. See how smooth and featureless these objects are. They're just big piles of stars. And here's another picture. Actually, for the purposes of our talk today, I think we're more interested in the other family of galaxies, the disk galaxies with spiral structure and spiral arms. Now, we know a lot about those disk galaxies. Why do I even call them disks? I mean, this one looks round. How do I know that that's a flattened structure? The reason is that we can see them, various ones, at different angles, at various inclinations. Some of them are face-on, like this one, and look round. Some are intermediate, and some, like our friend that we saw in a previous slide, are edge-on. And we know from studying their motions that these are rotating disks, and each star is in circular motion about the center of its galaxy. Now, what is a galaxy exactly? We haven't really explained that. To make that clearer, let's look at this picture. A picture actually taken by an amateur astronomer at a so-called star party. So amateurs get their telescopes together, they go to dark places. Here's an array of amateur telescopes all set up. This is a time exposure. And somebody thought to take a picture of the galaxy as it was setting in the evening in the sky over these telescopes. It's a nice composite picture because it gives us a sense of scale. If we could have much more sensitive eyes and look up at the sky, this is what the center of our galaxy would look like. And here's another picture which enlarges it. See, this little clump of stars has been enlarged to this one. This little red structure here is this structure here. And when you enlarge this part of the galaxy this way, see, it's full of salt and pepper grainy structure, and each one of those little grains is a star. So what this picture illustrates is that our Milky Way, of which our sun is a member in the outer parts, is a spiral disk galaxy just like others. We could put together a montage of the whole plane of the Milky Way, and we'd find a dust lane here that looks rather like the dust lane in our edge-on galaxy that we've been looking at, right? So this picture here in our galaxy would correspond to roughly that piece of the external galaxy. And we've studied the motions and the rotation of stars in our own galaxy, and we can tell that it actually is a rotating flattened disk like this external object. Okay, so there are a lot of stars in a galaxy, something on the order of 100 billion of them, and you get a sense of just a few of them here that are populating this picture of our own Milky Way. Now, I said a moment ago that galaxies were a very important way station on the formation of intelligent life. Why is that? It's because only in galaxies do stars form, stars and planets, because the rest of the universe is very dilute. And the density of objects of gas there is so low that you couldn't form a star. It's only where gravity has brought matter together in galaxies that the density is high enough. And we know that stars are forming actively in galaxies because many of them are blue. Stars that have recently formed, those populations are very blue, and you can see that this galaxy is full of blue stars. And you can take, with a special imaging camera, you can take a picture that shows star-forming regions called H2 regions. Here's an example. This is a picture with the Hubble Space Telescope zoomed in on this particular corner of a nearby neighbor. And this picture shows us two things: the clouds of gas, which are condensing to make the stars, gravity again, doing its work, pulling the interstellar medium together to make stars, and the newly born stars visible in a cluster right here. And it's lots of hot stars here exciting the gas from which they were born, making it glow, and that's why this gas appears in the picture. So you can learn a lot about star formation by looking at pictures like this. this is another Hubble picture of a piece of the Large Magellanic Cloud. And it's a nice picture because it shows various chapters in star formation all in one picture here. So here we see a newly formed cluster of blue stars, exciting gas around them. The gas is a mixture of regular gas and interstellar dust, and here's a blob of particularly dense gas and dust seen in silhouette. And in blobs like that, we can home in with Hubble and get really magnified views of what's going on. And we believe that stars are forming out of these incredibly dense, really tiny but very dense lumps of interstellar material. Now, I'm sure you've seen this picture. This is probably the most famous picture that was taken with the Hubble Telescope. The Hubble doesn't have a very big field of view, so it's kind of interesting to see this region, which is a star-forming region, in perspective. This is what the whole region looks like with a ground-based telescope. And here you can see, again, one of these huge interstellar gas clouds forming stars, and a clump of very hot blue stars has just formed over here, and their ultraviolet light is raining down on the interstellar medium and sculpting away the gas. And where the gas is dense, as here, it shields the gas behind it. And so the effect is to make these pillars. And the importance of this picture is to home in on this little area right here. Let's enlarge that. All right? And you can see the sculpting process has left behind denser regions. Imagine that rain was falling on sandstone rock and that there were hard, dense regions embedded in that rock. As the rain falls, it would wash away the softer rock and leave behind the dense regions. So we think that these little small globules here are regions inside the cloud that are particularly dense, and each one of those harbors a young star that's newly forming. Now we get further evidence that this picture that I'm telling you about is correct when we look in other directions, and we can see that the sculpting process has finished and actually revealed these dense structures, which are now silhouetted against glowing gas behind. And a selection of these is shown in the next slide. So each one of these is a forming star system, and we can see them at different stages of their development. And here's what they look like just when their star has fully formed. Here's the formed star, and here is a disk of gas, which is a proto-solar system, a proto-solar nebula that surrounds that newly born star. And in this particular case, we happen to see one that's edge-on, and the light of the parent star is just peeping out above and below the disk. And this whole thing is a structure that's about 17 times larger than our own solar system. These things are called proplids, which is short for protoplanetary disk. So thanks mostly to the Hubble Telescope and its very high resolution, we've actually managed to capture a whole family of stars in different regions of our galaxy in different processes of formation. Now, to go farther and really zoom down at high resolution in one of these disks, we don't have a telescope that will do that, so we have to resort to artists' conceptions. And here's a particularly nice one. All right? If we could look at one of those proplids at very high resolution in the center, this is what we would see. This is the newly formed star at the center, and leftover material is orbiting that star in a disk of gas. And that disk is busy making planets. It's full of rocks, rocky structures, which have condensed out of the gas. The rocks are composed of iron and silicon, carbon, and so on, just like the rocks on Earth. And those rocks, in turn, are drawing the gas in to make even larger planets. So this process is shown in the next animation, which takes us along a lot further in time. We started out with a disk that was quite full, and it's developing lumps. Now you can see planets spinning in it, and the planets are busy sweeping up all the material in the disk. And at the end, we have a bunch of planets in this system, and the last little leftovers of the disk are still there and may never get swept up. We can see evidence of that in our own solar system. In the outer part of our solar system, there's lots of material. It's the material that makes up comets. And it's sitting out there at the edge of the solar system beyond Pluto. And it's never been able to condense into a planet because it's too diffuse out there. It's not dense enough. So this is the basic picture that we have in mind now for the formation of stars, and after that, the formation of solar systems. And here, in yet another artist's conception, is a fly through one of these solar nebulae that's kind of middle-aged. So it's made one planet here, which is still busy sweeping up yet more gas and dust, but its protostellar disk is still full of rocky things like this. And the rocks are very important because it is thought they act as the seeds for drawing in the material and actually making the bigger planets. So planet formation starts with the condensation of these rocks, and then the rocks gather themselves together and also drag in more gas, and the net result is a planet. So how do we know that this is true? Well, we're finding out that our solar system is certainly not unique. This is the census as of a few months ago, 156 known extrasolar planets that now have been discovered by a variety of sensitive techniques. Each line here, or each column in this graph, is a star, and plotted next to the star is the distance of its planet from the star. The Earth would be somewhere on this line here. This is the Earth's distance from the sun. And you'll see that in some of these systems, there are actually multiple planets. There's not just one planet, but multiple planets. So we're beginning to find multiple solar systems. And if there's time and you want to ask me more about the characteristics of solar systems, I could tell you a few more details. All right, so I'm emphasizing the fact that rocks are very important. Now, most of the universe is not made of rocks. It's made of hydrogen and helium. You have to have heavier elements in order to make rocky stuff. You have to make rocks in order to make a terrestrial planet. We think you have to have rocks in order to make Jupiter, because the core of Jupiter is a rocky planet. So how do we get the material of these heavy elements in order to make the rocks? And that's where we have to refer to stars once again. Stars are needed to form solar systems, but they also are needed in order to make these heavy elements like silicon, carbon, and so on, out of which rocks are formed. Now, after a star forms, we really have a very good theory for what happens next. Our theory of stellar evolution is very well developed, and it's summarized in this diagram here. This diagram plots the surface temperature of a star. Hot is over here, cool is over here, versus the luminosity of the star. And the point of the diagram is simply that stars don't fall at random in a diagram like this. They follow certain patterns. And the main one is this one here, which is called the main sequence. Massive stars are up here, and little stars are down here, and the sun is right around the middle. It's probably right there. I think that says the word sun. So a massive star doesn't live very long. Even though it has lots of mass, it burns it quickly. It ages to become a supergiant, and then it goes down here to become a white dwarf, or it explodes. And then the sun is going to go up here into the giant branch and come down here and make a white dwarf. So the next movie actually animates this process. This is a movie on the web called 10,000 Stars. Okay? And it shows you how 10,000 stars, if they were all formed at exactly the same time, how they would evolve in this diagram. And what's happened here is that the early evolution goes very fast, and all of these massive stars have now disappeared, and stars like the sun we're about 5 billion years into this video now, are just now becoming giants, and after they become giants, they're evolving down here to become these burnt-out white dwarfs. So we can look at that again, okay, and focus on the early stages when the massive stars are still evolving. Because it's the massive stars that we really need to understand right now. They explode as supernovae. And when they explode, they spew their contents out into the interstellar medium. Here's a massive star just before it explodes as a supernova. It started out being mostly hydrogen. And in its outer layers, it's burned hydrogen to become helium. This is what happens in a hydrogen bomb. 4 hydrogens become a helium atom. But it's possible at slightly hotter temperatures, deeper in the star, to combine helium to make carbon and oxygen, and at higher temperatures burn carbon and oxygen to make neon and magnesium, oxygen and magnesium, silicon and sulfur, until finally we get to the core of the star, which is comprised of mostly iron. And then the process doesn't go any further to release energy. In fact, to go to even heavier elements consumes energy, and when the star tries to do that, its core collapses. This causes a supernova explosion. Paradoxically, the inside goes inside and the outer layers go out, and you get a massive supernova explosion, which, if you come back a few thousand years later, is making something that looks like the Crab Nebula, a supernova remnant. This is a cloud of gas that used to be the layers of that star, now expanding with a velocity of something like 2,000 or 3,000 miles every second. So these clouds that you see here in supernova remnants have lots of heavy elements that are going out into the interstellar medium, where they can be swept up in new generations of stars. And so as time goes on, the interstellar gas is always getting more and more heavier elements from each successive generation of stars that is born. And that process is summed up in this slide. Here's a galaxy. Here's a supernova that's going off in that galaxy, temporarily very bright, making a big explosion. The ejecta are going out into the interstellar medium, carrying oxygen, magnesium, and all those heavy elements, seeding the interstellar gas, which is making the next generation of new stars here, and the whole process is going to repeat. So as time goes on, we started out in the beginning with gas that didn't have heavy elements, but after a few, just about 1 billion or several billion years have gone by, now suddenly we have stars that contain more heavy elements. And the sun, which formed around 9 billion years after the beginning of the universe, has solar abundance of heavy elements, and that was enough to make a solar system. If you had a star with no heavy elements, it couldn't make a rocky planet like the Earth. So some time had to go by with nucleosynthesis before you could start making planets. And in the case of our sun, 8 billion years, 9 billion years of cosmic time, we managed to make our solar system with the Earth, Moon, Sun, and the other planets. So let's look for some confirmation of this. Here I'm going to tell you just very briefly about some of my own work. Hannah was kind enough to mention the fact that I'm an observer and I like to look out into space. And the advantage of that is looking out in space is also looking back in time. If you have a very strong telescope, which can look very far, it took billions of years for that light in order to reach us. So you actually see the objects back in time as they were billions of years ago. So this picture that I showed you before, that looks out to a quarter of the visible universe, covers maybe 22% of cosmic time. But we can look much farther if we have bigger telescopes looking to even larger distances. So the Hubble Telescope is an example of a telescope that has made very deep observations. This is the so-called Hubble ultra-deep field. Shown to scale here, here's a little patch of the universe. It spent hundreds of hours taking this picture, probably the most expensive picture ever taken in the history of the world. And it shows you to scale what that little patch looks like compared to the size of the moon. There was nothing special about this patch. All patches statistically look the same. The galaxies are different, but nevertheless, in general, their properties are statistically very similar, regardless of where you look. So here's a blow-up of that picture, the ultra-deep field. And now we encounter a problem. We would like to look back in time to see galaxies at different stages of their evolution, but we have a difficulty. The difficulty is that we can't look at pictures like this and say immediately how far away things are. We could probably say that these two big things are somewhat not too far away in the foreground, relatively near, and something that's tiny like that is probably farther away. But what do you do with something like that? The sizes of galaxies vary a lot, and so you can't just look at their apparent sizes in a picture like this and decide how far away or back in time you're looking. So you need a redshift. You need to take a spectrum in order to date them. And that's what our survey, called the Deep 2 survey, is doing. It's looking back, making core drillings of space, looking back in time. And the limit of our survey is just beyond the time when the Earth formed. We're looking about 9 billion years back in time, where the Big Bang was 13.5, and here's where the Sun and the Earth formed, okay, on this diagram. So our survey is looking well past the formation to earlier times before our solar system formed. This is the machine that we use in order to make a survey like this. It's called a spectrograph. It spreads the light of galaxies out into a spectrum. This particular spectrograph was built at my institution, Santa Cruz, UC Santa Cruz, called Deimos. This is a couple of pictures showing it in transit. Here it is in its shipping crate going to the big island of Hawaii. Going up the road to the top of the volcano called Mauna Kea, to be located in this telescope here called the Keck 2 telescope. It's sort of hard to get them into domes. You have to have a big crane to lift them up and put them inside. And finally, here is Deimos at home on a platform next to the big Keck telescope, which is 10 meters in diameter. So we thought it looked big in Santa Cruz, but by this time it's looking rather small. Here is one example of an exposure from this telescope. And it looks as though it's full of data, but don't be fooled. Most of those features are coming from the Earth's atmosphere. And if we blow up a little section like this, we can see that all of these features, these stripes, like this one and this one and this one, these come from air molecules. And they're just an interference. We have to subtract those away. So we have a process for doing that, and after cleaning up those lines, we're left with real features. These come from galaxies that are 9 billion light years away. And these are produced by oxygen atoms in those galaxies. So we're actually sensitive to the amount of heavy elements in the galaxies. You can measure lots of things for every galaxy. The general redshift tells you how far away the galaxy is. The bigger the spectral shift, the greater the distance. We can measure the total luminosity, the total color, the nature of the spectrum, which tells us the star formation history of the galaxy, its radius, its orbital speed. We can put those two numbers together to form the quantity v squared r to measure the total galaxy mass. And as I noted, we can measure the strength of that oxygen emission, so we can even trace the buildup of the heavy elements. So we're now actually watching galaxies build heavy elements billions of years back in time. And I can tell you from watching this process that the sun and the solar system formed just about as fast as they possibly could have. It took that long, 9 billion years, for the interstellar medium in our galaxy to get up to the point where the sun and the planets were actually able to form. Stars formed earlier than that, but planetary systems were very rare. So we are, in some sense, pioneers in our part of the galaxy, one of the first solar systems to have formed here. So recall, now I've almost ended my talk, I began by telling you about the ripples that created the structure via gravity, and I promised that before I ended my talk I'd come back to that subject and say a few words about where these ripples actually came from. So let's do that. We wish we could observe this process directly, but after all, this is 10 to the minus 35 seconds after the Big Bang. And so again, we have to resort to artist conceptions. Here's a typical chunk of the universe back then, right after the Big Bang. And I've drawn it in such a way as to suggest that its density is not quite uniform. That's the variations at a part in 100,000 that I was telling you about. If you could take a magnifying glass to a tiny patch of the universe, you would see, as a function of position, variations in the matter density. And those are the ripples, very tiny ones, I've exaggerated them here, that are the seeds of gravity. So where did those ripples come from? Well, this is where Einstein would have been really intrigued. We think that there's this special process at this very early time that creates the ripples out of quantum fluctuations. There's quantum fluctuations going on everywhere in space, and normally they don't do us any harm. They come from something called the Heisenberg uncertainty principle. It's a fundamental element of quantum mechanics, that there's statistical uncertainty in the state of matter. Now, those fluctuations, which are right here in this room, every little space in this room is subject to them, generally do us no harm, because a fluctuation arises, and as soon as it arises, it dies away. So on average, nothing happens. But in the early universe, when the early universe was expanding during this so-called inflationary period, right after the Big Bang, it was literally expanding faster than the speed of light. And when one of these little fluctuations formed, the universe expanded so fast that before the fluctuation could die away, it became a large fluctuation. And then it wasn't a quantum thing anymore. It couldn't disappear via quantum mechanics. It was frozen in. And so during this remarkable period that is a tiny fraction of a second, the universe expanded by many, many, many powers of 10. And every part of it was seeded with these tiny fluctuations, which lived for a time doing rather little, but after a passage of several 100,000 years began to drive gravity and make the galaxies. And so the really remarkable realization from modern cosmology is that all the galaxies were born from quantum fluctuations, including our own Milky Way. So it's a little ironic that I stand here as the first Einstein lecturer, because those of you who study Einstein and are familiar with his writings know that he was a lifelong skeptic about quantum mechanics. He found it very difficult to accept, and I think he'd be bemused today to understand that, or to see that the heart of cosmology, the formation of galaxies leading ultimately to the formation of life, depends critically on the truth of quantum mechanics. So, to summarize, here we have cosmic history in 4 easy steps. We have the Big Bang itself, which I haven't talked about. I've just assumed that it exists. And a tiny fraction of a second after that, there's this period of inflation, which creates the tiny ripples. Time goes by, nothing happens for a while, but after a few 100,000 years, gravity is able to kick in, and those ripples act as seeds for the formation of galaxies, the formation of stars, and 9 billion years later, finally, the formation of our solar system and our Earth. So that's the cosmic story that I wanted to tell you, and in the 2 or 3 minutes that I have left, I'll just mention a few interesting philosophical points. Why is this information useful? I think we would all agree that it is interesting. Somehow there's something about the human species that is interested in history and beginnings and causes. And we like to understand our roots and where we came from And these are our cosmic roots. But are there any morals here that we should pay more attention to, on which we could actually base our behavior? Now, here I have to confess to you that I'm not a religious person, so I don't look to Scripture for justifications as to what we should be doing, as to what is right and wrong, what is good and bad. And since I am such a person, I'm a little bit adrift when it comes to morality or statements of human beings should be doing this, that, and the other. Where does the should come from? So the best a person like me, I think, can do is to take refuge in who we are. I think that our feelings about right and wrong come from our genetic code. They come from the very species we are, and that this genetic code and its rules for right and wrong are our strategy for living in this world, and we better think twice if we disobey that strategy, because it's gotten us a long way. Now, one of the rules of our genetic code is a respect for the sacredness of human life. If a species didn't respect its own life, it would not be a successful species. It wouldn't be here today. So this is one of the requirements you need to have gotten this far. If you have a respect for human life, then it follows, in my mind, that you should be doing your utmost to protect it and to further it in the future. And I would even go beyond that and say that there is an additional moral imperative here that comes out of cosmology. The universe evidently is able to make entities that are incredibly complex. And one of the morals we learn from cosmology is that the rest of the universe is not that complex. But it has sown the seeds for a marvelous complexity on this planet. However, when we look out, we see that most places are not like this. Certainly stars are not like this. And the more we know about solar systems, even though we found them, we can see that solar systems with exactly our property might be quite rare. So we don't know yet, but in fact, finding a hospitable terrestrial planet like the Earth, it's not impossible, but it might not be that frequent. And then having gotten to a planet like that, it might not be inevitable at all to lead to a species like ourselves. Maybe eventually, but not in just as brief a time as 4.5 billion years. Now, if you believed, or if cosmology told you that the future was limited, then you would be free to live on this planet however you liked, using up its resources and polluting its atmosphere however you liked, because you would know you had no future. But my closing remarks here are to say that if we've learned anything from this history, understanding where the universe, how it started, how galaxies were made, how our sun was born, the real moral is that we have been incredibly fortunate. We got here about as fast as you could possibly imagine getting here. I haven't told you about the part of the story that continues from the formation of the solar system to now, but I think if we had a biologist here and a geologist, they would agree, too, that things went at an amazingly efficient clip. The good news is we were so lucky and so successful that our sun is only partway through its life. It has at least another 1 or 2 billion years to go, and I predict that we will have learned to engineer the solar system and move the planets around to compensate for the fact that the sun, as it ages, is getting a little hotter. It's not a big engineering job, believe it or not, to move the orbit of the Earth out a little bit, gradually over time, to keep it cool. If we took advantage of that, we have more than 1 or 2 billion years. So the real cosmic story is, how long has intelligent life been around? A few million years at most. That's a blink of an eye compared to the 1, 2, 3, maybe 4 billion years of cosmic time that the universe has allotted us. We're already a very interesting species, and I think it would be really tragic in some cosmic sense if we snuffed ourselves out in the first couple centuries after we inherited or devised the ability to do so. Because with the gift of time, our species could do great things, if only we can get to the future. Thank you.
Thank you, Sandy. Let's move right on to the questions. The stage is open.
Yes.
The lady with the microphone, please. You have one here. Coming up.
Is our sun a second-generation star, or I mean, how many supernovas is it estimated got together to make the stuff that puts?
Well, it's a continuous process, so it's not a discrete thing. But there were lots of stars before the sun. That's really about all I can say. The sun was extremely lucky in being very metal-rich. Astronomers refer to these heavy elements as metals. And if you go back to our solar neighborhood 5 billion years ago, we can do surveys of stars that are 5 billion years old, and we can measure their heavy element content. And the sun is more metal-rich than almost any of them. This happens because the interstellar medium isn't perfectly mixed. So at any given time, there are metal-rich patches and metal-poor patches. We were very lucky we came from a metal-rich patch. So, now I'm really ranging far afield. Maybe we need to take seriously this business of looking for planets around, or intelligent life around other stars. Maybe we are really pioneers. Maybe they're not here yet because we're the first. Maybe there's galactic politics in this. Think about this.
Yes.
You mentioned that the universe expanded faster than the speed of light. Isn't that a contradiction?
It actually isn't. Things can't go faster than the speed of light when they're close together in the same rest frame. But if gravity is pulling differentially on them, then gravity can pull things apart faster than the speed of light. And who's the person who asked? There you are, okay. And so here's a familiar example. You've probably heard of a black hole. A black hole is black because as things fall into it, they accelerate faster than the speed of light. So they disappear as they approach this magic radius called the Schwarzschild horizon. Now, the only trick is that time appears to slow down when things accelerate to the speed of light. And so from our vantage point outside the black hole, you never actually see the object fall into the black hole. It gets closer and closer to this magic radius, but never actually quite goes over it. It goes out. You get fewer photons from it. It disappears, but you never actually see it fall inside. The same thing is happening in this magic period called inflation. Inflation is like an inside-out black hole. It's a universe that's expanding out the way matter would fall into a black hole. And so if you and I were in that universe next to one another, you would accelerate away from me, approaching the speed of light. But as I view you, anything to do with you, like your watch or whatever was happening in your environment, would slow down. Time would slow down, and I'd never actually see you disappear. So I can't ever actually see things going faster than the speed of light, even though the space really is expanding faster than the speed of light.
Yes, please.
Hello. I wanted to know if the scientists have any idea what happened before the 1 to the, what is it, the 10 to the 35th second.
10 to the minus 35 seconds.
I was there. Did it start from no matter that became matter into this little spot that expanded into the galaxies in the universe, or do they have any ideas about what happened?
There are speculations, and again, that would be a wonderful topic for this lecture series. I'm not really the person to hold forth on that. But there are several ways of thinking about this. There's a thought that there is an underlying entity called an inflaton field, which is just an energy density subject to quantum fluctuations. And the story I told you was kind of a classic story that involves these quantum fluctuations after the universe actually begins. But an even more bizarre form takes this pre-existing field and makes the whole universe out of it. And such a field could give birth to many baby universes in different regions, which would then expand apart from one another faster than the speed of light, and you'd never know that they were there. So perhaps the most intriguing idea is that actually nature has a way of churning out an infinitude of universes. And there's a big question as to whether they would all be like ours or they might all be quite different. And maybe we're here in our universe just because it's hospitable to our form of life, the way the Earth is hospitable to our form of life. And maybe there's different intelligent life in other universes with different laws of physics. You can read books about this, popular books.
It's called the anthropic principle in some places.
Right.
Yes?
I notice you're on the SETI Institute, that you're on the board there. How would you distinguish if you really received some kind of a message or some kind of a coherent message from outer space, and because of all the noise coming in, and how would you distinguish it, and how would you know that it is something?
Well, that's a real good question. The people at the SETI Institute have spent an awful lot of time thinking about that. But the key thing that they are looking for is something that has a very well-defined frequency. And they know how the Earth turns and how it goes around the sun. And so they know how frequencies of an outer space object should vary if it's really out of our solar system. And so when they look for these external signals, they're looking for signals that have the right frequency behavior as a function of time. Most of the noise originates here on the Earth and doesn't have the right frequency behavior. So they can actually throw away most of it. Another trick they use is to have two telescopes that are separated by a lot. And two telescopes have different noise backgrounds. And if they see the same signal, that's further evidence. They have fancy computer programs that look for these characteristics.
As a biologist, I was very fascinated by your review of cosmology, but I hope I did not understand some of your remarks about biology.
Okay.
And particularly the ones in which you search for morality in our genes. For instance, when they give me one example, if the Hutus wiped out the Tutsi in Rwanda, this was completely conforming to our genetic must, and we were doing things genetically. I mean, there was starvation in Africa, and it's a very good biological evolutionary way to have half of one population destroy the other half. Is that moral?
No. So it's obvious that there's a selfish imperative in our genome, and there's also an unselfish imperative. And as we got here, the strategy that has worked best for us, I think, is some balance between those two, occasional warfare versus occasional cooperation. A very interesting question going forward is whether that mixture of strategies is the right mixture for the future. And I chose in my talk to emphasize the unselfish aspects, because I think that's the strategy we need in order to see us through at least the next few hundred years to solve the problem of resource allocation on this planet. And it would be too bad if we are the prisoners of our genome to the extent that we can't adapt to a new situation and in fact snuff ourselves out just because we can't adapt. But I'm not disagreeing with you.
Yes, please.
If the quantum fluctuations are happening everywhere, why would inflation affect this space differently than another part of space.
If this space here suddenly began inflating, we'd have the same process. Okay, so I think I don't want to put a question in your mouth, but I think the real question you're asking is why was there inflation then and there's not now?
No,
No, that's not what you want.
why would it affect this space to be with more dense than a different piece of space?
Imagine a little machine which is generating density fluctuations, and there's a little machine right here and there's a little machine next door. Every little piece of space is doing this. And now make that whole pattern expand in a blink of an eye such that all the little density fluctuations now become bigger and they are now too large to disappear by quantum mechanics. So suddenly we have a snapshot of something that was very small now blown up to something that's much larger. Not sure I'm really answering your question. Do you? Is that good enough? Yeah, okay.
Raymond?
Well, I thought you gave a very lucid description of the origins of the universe. Would you like to say a few words about the origins of the laws that govern the origins of the universe?
Right, yes. Yes, but my problem as a cosmologist is now no longer answering what our universe looks like, but rather what can a universe look like. And I referred a little while ago to this incredible machine which might be out there generating universes. First of all, we don't know that there's that machine, but even if there is, we really don't know very well what kind of universes it's actually making. I ask my physics friends that question, and most people say, first of all, we don't know, but they also say that they believe that there is the possibility in this process of making things in all different ways, so that there might be universes with more dimensions, or universes without matter and something else. So I think that you might get a handle on this if you understood something called string theory and understood what string theory could make. Then you'd be on your way to understanding how different all these universes might look. But you're way over my head now.
Amri?
Well, hi, Sandy. I just want to comment on one of your statements that we are as lucky as could be regarding time the life evolved on Earth. I think the galaxy exists for about 10 billion years, and the first generation of stars with enriched interstellar matter and so on could have been earlier. So in a few billion years you would already have, there could have been, what I want to say that why couldn't we have stars that would have evolved planets and so on 1 billion or 2 billion years earlier than we are, even in our own galaxy.
Absolutely. And you probably didn't notice it, but as I said those sentences, I was very careful. So let me reiterate how I was being careful. What I said was in our part of the galaxy, in our solar neighborhood, our ring around the galaxy. You've raised a really good point, and that is that astronomers are able to look at different parts of galaxies, our own and external, and measure the heavy element abundances of the stars in them. And galaxies seem to show a general pattern. The stars in the middle have higher heavy element abundances and the stars in the outer parts lower. So as we look to the center of our Milky Way, I was showing you pictures of that, those stars are actually more metal rich. And I think there's a real possibility that there are lots of solar systems. If you're going to go looking for intelligent life in our galaxy, that's where you would go, the center.
I think we can conclude here. My impression is that the questions were especially interesting today, maybe indicating a correlation between intelligent life and English speaking. Thank you very much, Sandy.
Thank you.